A satellite can measure the ocean by timing radar pulses as they bounce from the sea surface, but it must correct for waves, air, and Earth's shape. How do we turn a beam of light into a measurement accurate down to a single millimeter? Imagine standing on a high bridge and dropping a tennis ball to figure out how high you are. You drop the ball, time how long it takes to hit the ground, and do some quick math. A satellite does the exact same thing, but on a massive scale. Flying about 800 miles above Earth, it shoots rapid radar pulses down to the sea. It times how fast they bounce back. Since we know the speed of light, we can calculate the distance. But here is where it gets crazy. To track climate change, scientists need to measure changes as tiny as a single millimeter. That is about the thickness of a credit card. How do you measure a credit card's thickness from space when the surface below is covered in massive crashing waves? If you just timed a single bounce, a 10-foot wave would make the ocean look much higher than it actually is. To fix this, the satellite does not just look at one bounce. It fires thousands of pulses every single second. It averages them out to digitally smooth the waves away. But that opens up a much bigger problem. How does the satellite know exactly where it is? If the satellite wobbles in its orbit by even an inch, the entire measurement is ruined. To solve this, scientists track the satellite using ground-based lasers and GPS. They map its orbit so precisely they know its position down to a fraction of an inch. Now you might think, once we know the satellite's position and the distance to the water, we finally have our sea level. But there is a giant trap. Most people think the ocean is perfectly flat, like water in a giant bathtub. It is not. The ocean's surface is actually full of permanent hills and valleys. Undersea mountains have heavy gravity that pulls water toward them, creating massive mounds of water on the surface. Deep ocean trenches have less gravity, so the water dips down. The sea is literally warped by Earth's lumpy gravity. On top of that, the air itself messes with the radar. Water vapor in the atmosphere slows down the radar beam. If scientists did not correct for this humid air, the delay would make it look like the sea level is lower than it really is. So the satellite carries an onboard instrument that measures the water vapor in its path. It calculates the delay and corrects the clock. Only when you combine all of these things, the laser orbit tracking, the gravity map of the Earth, and the wet air corrections, do we get the true height of the ocean. If the ocean's surface is shaped so heavily by gravity, what does that mean for how sea level rise actually impacts different coastlines around the world?